Our next speaker is Jerry Carson. Jerry Carson holds a BSME from the U.S. Naval Academy and a master's mechanical engineering from George Washington University. He served 4 years at sea, and after leaving the service, worked in aerospace, marine, civil, and defense industries. Jerry is currently a graduate research assistant at University of Maryland, helping to develop direct fusion drive. So he's going to be talking about direct fusion drive based on centrifugal mirror confinement.
Thanks,
Jerry.
Good afternoon. The University of Maryland Space Power and Propulsion Laboratory has a team that is working on different parts of this idea. It's a different architecture from some of the ideas we've seen earlier this week. I've got more of the systems view. We have several teammates, and I'll talk about what some of those teammates are doing in different parts of the system a little bit later. But I think the common idea of a fusion drive is you get a lot of jet power out of it, and that's important. That gives you a lot of flexibility in what missions you can accomplish. But obviously, there's a lot of technology that needs to be developed, and this is one particular approach that we think has some promise, and I'll talk about what centrifugal mirror confinement is, just as we go forward. But before we do that, hit on some preliminary ideas to get level set on some terminology, and then we'll move into a discussion of centrifugal mirrors as a method of containing plasmas, and then how we might apply that to a propulsion system and what capabilities that brings to relatively near-term missions, or I'd say near-term, the next 10 to 20 to 30 years. Not necessarily extrastellar at this point, but the very high jet powers do give you capability that you may not get with nuclear, electric, or certainly with chemicals. Dr. Ray Sedgwick is the principal investigator on this task, and the task is being funded by the Limitless Space Institute, so I appreciate their support here. Our goal is to get to a technology readiness level of 3. That's going to be based on the analysis that we go through to prove out the concept in theory. And also, we are working in collaboration with our physics department and the University of Maryland, Baltimore County, as they go forward with an experiment using centrifugal mirror confinement to actually achieve fusion conditions, and I'll talk about that experiment a little bit as well. So fusion, plasmas are hot ionized gas, and the electrons and ions, they are electrically conductive. So that gives us a couple of knobs to turn in terms of using electric fields and magnetic fields. But controllable is a relative thing. There's a lot of stuff we don't understand. And even this particular method, which you think has a lot of promise, there are some issues that we're still working through. But obviously, if you're doing even though the plasmas are relatively rarefied, they're still tens of thousands to several million degrees Kelvin, or more convenient measure is electron volts, or MEVs. Plasma systems are already being used for propulsion systems. Hall thrusters used for station keeping in low Earth orbit. Been a fair amount of research done on magnetoplasma dynamic thrusters, particularly at Glenn, early 2000s. And then, of course, there's Ad Astra's entry that is using ICH, cyclotron heating, to actually heat the ions up. And that's a different approach, because most of the time we think about hot electrons, not hot ions. And so their system's a little bit different. But what we're going to be talking about today is a system that actually allows us to use thermonuclear fusion to heat that plasma instead of an electrical or other type of method. So as Dr. White talked about earlier this morning, we're not splitting uranium or plutonium atoms. We're fusing light nuclei. Deuterium, tritium is our baseline analysis. We're more interested possibly moving on to helium-3 and deuterium, just because of the neutrons and what we can do with those, or what we can't do with those in some cases. But right now, the first pass is on a DT system. There is an important factor, not only temperature and pressure, but how long you can keep those species contained. A confinement time, we're aiming for confinement times of 10 to 20s of seconds, which is way up from the milliseconds range that you're typically going to see in a mirror device. A mirror device is a type of magnetic confinement. The other types of containment are like inertial devices, and we've heard a bit about those as well. And then there's the MTF, which is sort of in between. But the nice thing about a centrifugal mirror is it augments the otherwise leaky nature of mirror containment with the centrifugal component, which gives you a fair amount of, we believe, a fair amount of confinement. It reduces losses in the well, and it allows us to achieve the lossing criterion a little bit better. The high velocities that go with the centrifugal confinement also help to suppress stabilities that bedevil a lot of plasma machines, and the shear heating also adds to the heat balance. So a drift velocity, this is our secret sauce. I think this is the only equation I have in the briefing. This is the description of the drift velocity. In the limit is essentially the electric field strength divided by the magnetic field strength. And drift is a misnomer because it can actually be several millions of meters per second spinning around this annulus, and that helps to confine the plasma both radially and axially. If you look in the bottom right-hand side, what you're seeing there is the two great things are the mirror magnets. And under normal circumstances, in the absence of electric field, these mirror magnets can contain the plasma up to a point. The charged species will bounce back and forth on the lines of force between the two magnets, hence the name mirror. But mirrors are inherently leaky, as I mentioned, and the early promise of this type of technology that was pursued in the 50s fizzled out because they just couldn't maintain the plasma because of the leakiness. So we added another knob, which was this electric field, which comes out of that central electrode. What you're looking at is the upper half of a cylindrical reactor, and that bottom dotted line is a center line, and there's a negatively biased electrode there which imposes this electric field. And between the magnetic field and the electric field, you get this E cross B drift, which causes this very rapidly spinning donut around the axis and contains the plasma. If you look at the colored on your left, that's a simulation of that process. It's a solution of the momentum equation. And you can see that the white space is a Mach 6 type of velocity there, and you can see that particular blob of plasma is confined both axially as well as radially. So centrifugal mirrors have a somewhat of a history going back to the 50s and the 60s in the United States. The Ixion machine demonstrated the process. Sweden had a very extensive program with this in the 60s and 70s that with their F1 and F3 machines. In fact, the original idea of achieving fusion conditions was by B. Leonard, who built the F1 and F3 machines. And then the Soviet Union, they built the PSP2 machine, which is very similar in design as to the F3. In the early 2000s, the University of Maryland built the Maryland confinement experiment, which demonstrated the ability to confine plasmas, again, using mirror confinement. And they were able to confine 100 eV plasma. And just for reference, 1 electron volt is about 12,000 degrees Kelvin. So when you're talking about tens of thousands of electron volts, it's pretty toasty. So right now, as I mentioned, the University of Maryland and the University of Maryland, Baltimore County are in collaboration with a follow-on to the MCX. It's the Centrifugal Mirror Fusion Experiment. That's a picture of it there. That's on the campus at College Park. The principal investigator is Dr. Carlos Romero Talamas of UMBC. And he has a cadre of folks from both campuses helping him build that machine. They're at initial operating capability right now. They're principally doing hydrogen experiments and calibrating their instruments and building their instruments. One of them is going to be a neutron detector for when they get to deuterium plasma next year. And so they hope to achieve fusion conditions. And that neutron detection device is going to be how they're going to demonstrate how much fusion they got. So we've got this idea of a centrifugally confined plasma where you can achieve fusion conditions. For terrestrial purposes, that's what the CMFX is primarily concerned with. You want to minimize the amount of momentum loss out of either end of those mirrors. In a propulsion application, we actually like to get a little bit out, and that's what's going to be part of our propulsion system. But instead of just passing high-speed alphas to the vacuum and getting a lot of specific impulse, but a very little thrust out, we're going to do that. We're going to put this reactor in tandem with a warm plasma, which is essentially a reservoir of hydrogen, or it could be another gas. The fusion products leaving the well will enter the warm plasma. They'll deposit their heat primarily on the electrons. And that heated warm plasma will pass out through a magnetic nozzle. And you can basically, I would say, dial your thrust versus specific impulse, but you have some flexibility of what that mix is. We have a factor we call chi beta, which is the ratio of the propellant species in particles per second to the prompt fusion species, the alphas in particles per second. And for realistic systems to get to 10,000 to 20,000 to 30,000 seconds of specific impulse and a few newtons, which translates to hundreds of maybe 1,000 kilowatts of jet power, you need 10,000 to 20,000 to 30,000 values of chi beta, which essentially means you're putting that much more propellant into the system than you're getting out of the reactor in terms of hot fusion products. And again, there are some places where you want to have more fusion, more thrust. In other places, you might want to have more specific impulse, depending on the mission. But there's another purpose for having this warm plasma. There's concern with what's called the frozen end theorem, that charged species have a difficult time detaching themselves from magnetic fields. One way to do that is have a more collisional plasma where the particles interacting with each other can help bump each other off those fields. That's not the case in a straight fusion plasma. So the warm plasma also adds that collisionality to the plasma when it leaves the nozzle so that it can detach and generate thrust. We use the material leaving from the upstream part of the reactor to power the reactor. So this is a self-powering system. This is a schematic. It's not as fancy or as well developed as some of the other schematics we've seen this week, but you can see the mirror magnets, and that blue region is the electric field. And we have the well of the reactor, those two red things, just think of as a cross sections of a donut, and the high energy species passing to the warm plasma on the aft side, and the high energy species passing to the direct energy conversion on the forward side. We have in the baseline of the case I'm using, a standing wave direct energy conversion. There are other ways of doing it. In fact, my colleague Tom Bone will be talking tomorrow about using neutrons from the reaction in PB11 types of reactors to generate Bremsstrahlung, and then to use that to power the reactor. So we're very concerned about having a self-powered system. That's a very key component, and that's driven us to places in the operational space that our terrestrial friends may not be as interested in. But the baseline idea of a SW deck, the idea there is you modulate the alphas coming out of the front end into these packets, and then they go through this essentially a particle accelerator, and it recovers the energy. Instead of accelerating the particles are slowed down and they generate power, and then we do some voltage multipliers and then provide the bias back to that central electrode. And we've done the analysis to show that under certain circumstances, you can achieve that energy balance. This is some representative performance figures, and it shows the relationship between the specific impulse and the thrust that you get out of these for a given jet power. The curve on your left is the specific impulse, and the x-axis on both is the chi beta, the propellant proportion. And again, large numbers, 50 to 60, 70,000 for a 10,000 second ISP. And you see as the ISP, as the chi beta gets smaller, the ISP gets larger, but the thrust, as you see on the right-hand side, gets lower. Those three curves are a megawatt at the top, 500 kW in the middle, and then 100 kW on the bottom. And we're talking 1 to 2 to 10 newtons of thrust for a given system for these power systems. So that's pretty significant for a long haul operation. And we are talking about continuous operation for the most part. And that has some fairly important implications for the mission analysis or the mission design. The graphic here, the one on the upper left is you may not be able to see it, but the red segments are where you have the engine on. That's a conventional, either thermonuclear or chemical plant where you have a burn at the beginning, you have a burn at the end. You might have a mid-course burn somewhere in there, but for the most part, you're just coasting along a conic section. The lower right is the trajectory that you would get from, or a cartoon of a trajectory you would get from a direct fusion drive operating continuously. You see the curvature somewhat suppressed. Some of the simulations we run once you get out past Jupiter just end up becoming a straight AT squared over 2 straight line. And that's with a relatively low level of acceleration, but over time, that adds to the velocity, and you can achieve not relativistic velocities, but velocities that will get you places fairly quickly within the solar system. So, just to recap: moderate thrust 1 to 10 newtons, high specific impulses over 10,000 seconds, theoretically up to 30 or 40,000 seconds, and high jet power. Low end is 100 kW. You can have some very attractive science missions for 100 kW. You can move people around the solar system for a megawatt. And then you can do also some interesting things with interstellar probes for values that are in between. So recap, we want multi-megawatt power generation, high specific impulse, moderate thrust levels, and a low system-specific mass. And this is one of our interests, is building up some idea of what the kilograms per kilowatt are. A representative benchmark right now is 40 kilograms per kilowatt for an electric propulsion system. We would like to get down to 20. That's moderately ambitious, but and some of our analyses are based on that kind of calculation. A direct fusion drive could get to Mars in 3 months round trip, and Saturn less than 3 years. And by comparison, a nuclear electric would take 10 months for the Mars mission and 5 years for Saturn. The Uranus Orbiter and Probe, currently proposed as a flagship mission in the recent decadal study, is expected would take 12 years to get to Uranus with a gravity assist from Jupiter. A probe to Neptune with an orbiter and 4 atmospheric probes could get to the more distant Neptune in 3 to 4 years. Similarly, the Interstellar probe, which is currently under study by NASA, is looking at a Voyager-class payload, getting to 1,000 astronomical units, the edge of the heliosphere in 50 years. A 250 kW DFD plant could deliver the same payload in about 30 to 35 years, a second generation. And finally, going forward, we're currently modeling the warm plasma right now to get a better idea, a finite idea of what the actual energy deposition is of these fusion products when they enter the warm plasma. We're analyzing the magnetic field for plume detachment, and we're trying to characterize the propulsion system mass to get us a little bit more fidelity on what we actually are dealing with in terms of system mass. And once we get that first pass done, we're going to revisit the whole thing with the deuterium helium-3 mix. So the other teammates, again, just briefly, we're talking high temperature superconducting magnet thermal design. These are our team members who are working on different parts of the problem. Standing wave direct energy conversion modeling, phase space modeling of the alpha interactions within the reactor plasma. And again, Tom will be talking about thermionic energy conversion using Bremsstrahlung tomorrow, and then shielding requirements for CM reactors. So that's what our team is doing now, in addition to the system level work I'm doing. So again, open to any questions, and again, would like to express gratitude for the Limitless Space Institute for funding this research.
And we do have time for questions. This gentleman over here.
Hi. Oh, I was wondering if you had any idea about the radiation thermal deposition into the electrical elements, the anode and the cathode.
Yeah, I mean, this is right now the one of the reasons we're going to He3 and deuterium is to get away from the neutron problem. But that's a significant engineering problem that we hope to have. We have had some of our team members look at the shielding requirements, but the actual answer is going to be probably some different technology for things like the superconducting tape and for the electrode itself.
Question? Here.
Well, let's get set. Could he or
Yeah. So obviously people have made fusion work inside bombs by using fission as a step to get the bomb to ignite, fusion igniting the bomb. I was wondering why in the space application for fusion, why people haven't really looked at using fission. It's a part of the process to get the fusion going. If there's a political reason or a physics reason.
One of the reasons is we're solving the problem we know how to solve. So just to give you a benchmark, another entry into this field, Princeton Satellite Systems actually has a patent on how they expect to start their field reverse configuration fusion engine. It's it is going to require a lot of energy. Right now, when we start the reactor at Maryland, there are a lot of transients that take a lot of power initially, and then when we get the voltage breakdown, it drops. So we do expect that there is going to be an auxiliary, nuclear reactor somewhere in there. The visual I showed on the Neptune probe had a little shell sticking out the back of the reactor deck, and that would have been a nuclear power plant, a small one, for auxiliary power. So there is going to have to be something along those lines. Unfortunately, the power electronics are the key there. Whether it's a Cockcroft-Walton or just some superconductors, the idea is you're probably going to have a buildup of charge over time, and then a start event, for this.
So I have the answer to your question, and I have a question for you. The answer to your question is there is a hybrid fission fusion propulsion concept called PUF, pulse fission fusion, that is spearheaded by Rob Adams and Jason Kasibia at University of Alabama, Huntsville, and Marshall Space Flight Center that look into that exact idea. The question I have actually is, in your system study, what efficiency are you assuming in the electrical conversion efficiency from the input electricity to the heat generated?
So the SW deck, and there's one of the references in the back of the package is on the SW deck is a fellow named Chap, and Ray Sedgwick actually wrote a paper on it, and they're expecting like an 80% conversion efficiency. Oh, in the propulsion direction?
No, the electricity stored on board to make fusion conditions happen. So the electric field, the voltage, the currents. And
so that's what the SW deck is. And the gentleman here asked the question about starting, and I sort of punted that to power electronics we haven't developed yet. But in the operation, the SW deck is one answer where we are pushing these very high energy alphas out the front end, not the back end for propulsion, but out the front end. And they go into this particle accelerator in reverse. And as the field slows them down, the electrodes recover the power from that, then it's put back into the system. Now, the problem we haven't really addressed a lot is that this is a low amperage system, but it's a very high electric field and voltage system. And how do we get to that electric field? We haven't solved that yet. And I would mention the numbers I talked about in terms of planetary missions for direct fusion drives were Jason Casabre's numbers.
Time for one more. Well, quick question. You're using helium-3. Have you looked at the availability of helium-3?
So right now we're doing deuterium tritium, but helium-3 and deuterium is a preferred fuel just from the standpoint of the neutrons that you do or do not produce. I think we're looking for helium-3 the same place everyone else is looking for, is in the regolith on the moon.
Right.
So there's obviously a growth industry. If you know anyone who's doing a startup there, you might want to buy stock now.
All right. Well, thank you so much.
All right, thank you.